What would happen if you fell into the most dangerous object in the universe? Would you die instantly or experience something entirely different? To answer that, we have to look at how they are born. When a massive star, one many times larger than our sun, burns through its nuclear fuel, it dies. Its core collapses inward under its own crushing weight, leaving behind a dead, ultra-dense corpse. You cannot see a black hole directly. They are invisible against the dark canvas of space. You cannot see them directly, but you can see how they violently bend and drag everything around them. If you were an astronaut drifting toward one, the first thing you'd notice is the stars behind it. Their light curves and warps, like heat rising off asphalt. The massive gravity is physically bending the path of the starlight. As you get closer, you experience gravitational time dilation. The deeper you go, the slower your clock ticks. To a distant observer, your clock nearly stops. You appear to freeze, your image fading and turning red as the escaping light loses energy. But to you, everything feels completely normal. Your reality and your friend's reality have completely fractured. Time is no longer a shared constant. Near a black hole, the passage of time depends entirely on where you are standing. Eventually, you reach it, the event horizon. The event horizon is the exact boundary where the escape velocity required to leave the black hole finally exceeds the speed of light. Since nothing can travel faster than light, nothing can leave. There is no physical wall here, no surface you can touch or crash into. It is simply a mathematical line drawn in empty space. As you drift across that line, you feel absolutely nothing. No alarm sound inside your helmet. The view doesn't suddenly go dark. This inescapable curvature of space was mathematically predicted by Albert Einstein's theory of general relativity, decades before astronomers could actually observe it. You have crossed the edge of the known universe, sealing your doom, and your body doesn't even register that it has happened. The physical danger becomes apparent as you fall deeper. Gravity gets stronger the closer you get to the center, meaning the downward pull on your feet is significantly harder than the pull on your head. This diagram illustrates the result, a process physicists call spaghettification. The extreme difference in gravity stretches your body vertically, while simultaneously compressing it horizontally, pulling you apart atom by atom. If you fall into a small black hole, these tidal forces are so aggressive that you are torn apart long before you even reach the event horizon. But in a supermassive black hole, the crossing is incredibly gentle. We have one of these giants in our own neighborhood. Sagittarius A star sits exactly 26,000 light-years away at the center of the Milky Way, packing the mass of 4 million suns into a space smaller than our solar system. To capture that glowing shadow, scientists use the Event Horizon Telescope, a global network of radio observatories synchronized to act as a single Earth-sized camera. While Sagittarius A star is massive enough to let you cross its horizon alive, that is a false comfort. Surviving the entry merely buys you a little extra time before the tidal forces destroy you deeper inside. At the absolute core of the black hole lies the singularity. This is a point of infinite density and infinite gravity, where all the mass of the collapsed star is crushed into zero volume. At this exact mathematical point, the known laws of physics cease to apply. Human scientific equations completely break down, unable to describe what happens when space and time are bent this severely. Every coordinate of the singularity represents a physical dead end for our understanding of nature. Here, our mathematics reaches an absolute limit. Stephen Hawking proved that black holes do not last forever. Over trillions of years, they leak quantum particles, a process known as Hawking radiation, causing them to slowly evaporate and shrink into nothingness. This creates the information paradox, a fundamental conflict in physics, asking whether your quantum identity, the information that makes up your particles, is permanently erased from the universe when the black hole finally evaporates. General relativity provides a mathematical solution known as an Einstein-Rosen bridge. This structure functions as a tunnel connecting two separate, distant regions of space. There is even a hypothesis that the matter crushed inside doesn't disappear, but acts as a cosmic seed. It could trigger a new Big Bang, giving birth to an entirely new universe on the other side. These objects provide the most extreme environments ever observed. If our own Big Bang began as a singularity, then the collapse of matter inside these holes may provide the only surviving evidence of the mechanisms that created our universe.